Alright, welcome to the class. Today we're going to have a look at the last topic of chapter 4, structure and properties of solids. The rising cost of fuel has had a profound impact on the price we pay to travel. You are likely aware of how expensive gasoline is these days. Now imagine the cost of filling a commercial airplane's fuel tank, which is 3,000 times larger than a car's gas tank. Given how much fuel an airplane consumes, it's not surprising that the cost of an airline ticket has increased substantially in recent days. Because of high fuel prices, airplane designers have been working to develop lighter, quieter, and more fuel-efficient airplanes, such as Boeing 787 Dreamliner's aircraft. This model plane uses approximately 20% less fuel than a comparable Boeing 767 model. The 787 Dreamliner is the first major airplane to use composite materials made from two or more substances that have significantly different chemical and physical properties. In composite materials, the substances remain separate and distinct from each other. Many common products such as boats, bricks, surfboards, and even concrete use composite materials. The 787 Dreamliner is made up at least 50% composite materials, being mostly carbon and reinforced plastic. The combination provides a high strength-to-weight ratio and makes airplane lighter than other models. Composite materials are also resistant to corrosion, heat, and chemicals, ideal for high atmosphere travel. The properties of a composite material are determined by the structural and bonding characteristics of the substances from which it is made. In this lesson, we will learn about the structural and bonding characteristics of substances in the solid phase. There are many different types of solids, such as ionic solids, metallic solids, molecular solids, and network solids. These are all crystalline solids. Figure 2 here shows 3 types of crystalline solids. You can see that the structural properties of each solid are different from each other. For example, as shown here in figure 2a, sodium chloride is an ionic solid composed of alternating sodium and chloride ions. And in figure 2b, diamond is a solid arrangement of carbon atoms. And then figure 2c, ice is a solid form of water. So note that the blue dotted lines here show hydrogen bonds between adjacent polar water molecules. You are already familiar with ionic crystals because we have studied the ionic bond that forms between sodium and chloride ions. This ionic crystal forms from the interaction of metal and non-metal ions, such as sodium and chloride ions. The ions arrange in a crystal lattice with alternating packing of the positive and negative ions, which is shown here in figure 2a. Many of the physical properties of sodium chloride are also characteristic of other ionic crystals. For example, sodium chloride is a hard, brittle solid. When it's dissolved in water, the solution conducts electricity, but solid sodium chloride does not conduct electricity. Ionic crystals tend to have high melting points. Magnesium oxide, which is used in antacid tablets, is an ionic solid that has a melting point of 2852 degrees Celsius. This property is a result of the strong ionic bonds that hold the oppositely charged ions together. To contrast, next let's have a look at the metallic crystals. If you had the task of describing a metal, what words would you use? You might say that a metal is shiny or silvery. You might also describe a metal as good conductor of thermal energy and electricity, right? In the solid state, metals form a metallic crystal, which is a structure composed of closely packed items held together by electrostatic interactions and free moving electrons. Unlike ionic crystals, not all metallic crystals have similar properties. For example, solid gold is quite soft and easily molded, making it useful in making jewelry. In contrast, solid aluminum, which is used to make items such as soft drink cans, is much harder than gold, so it keeps its shape better than gold. The melting points of metallic crystals also vary widely. Some metals, such as mercury, melt below room temperature, whereas others, such as tungsten, melt at temperatures higher than 3000 degrees Celsius. So what theory can explain these very characteristics of metallic crystals? The electron C theory postulates that metals are composed of closely packed items whose valence electrons are free to move. In this model, the positively charged nuclei of the atoms in the crystal remain at fixed points, while the electrons are mobile. And this concept is illustrated here in figure 3. So imagine that we have placed several small marbles in the cup of water. The water, which is representing the electrons, can move freely in the cup, but the marbles representing nuclei remain relatively fixed in space. The mobile electrons do not associate with one nucleus only, but move from the nuclei to nucleus and thereby hold the positively charged nuclei together. This theory explains the metallic bonding, the bonding that holds the nuclei and electrons of metals together. So the electron C theory explains several properties of metallic crystals. The atoms within metallic crystals have low ionization energies because they possess loosely held electrons that can move freely outside their valence orbitals. The strong forces of attraction between the positive nuclei and the electrons result in closely packed metallic crystal structures. So you can have a look at the table 1 here, which lists examples of common properties of metallic solids and explanation of these properties. Okay, if we finish, let's have a look at the next types of substances, which is molecular crystals. Some substances called molecular crystals form crystal lattice structures when in the solid state, including sulfur, iodine, water, and carbon dioxide. Molecular crystals are similar to ionic crystals lattice, except that they are often more complex. For example, the molecular crystal of water can form several different types of structures in the frozen form, which is ice. So figure 4 here shows a symmetrical hexagonal structure that is often the form of ice in a snowflake. The intermolecular forces within a molecular crystal determine its structure and properties. Remember that intramolecular forces are much stronger than intermolecular forces, right? So we have also studied that intermolecular forces include London dispersion, dipole, and a special dipole, which is called hydrogen bonding forces. Polar molecules exhibit both dipole forces and London dispersion forces, and nonpolar molecules exhibit only London dispersion forces. The weak intermolecular forces help determine the properties of neutral molecules, which is why molecular crystals tend to have lower melting points and be less hard than ionic crystals. Molecular crystals contain neutral molecules, so they do not conduct an electron current very well, either in their pure form or in solution. So you can have a look at table 2 here, which lists the main properties of molecular crystals. And also figure 5 here on the top left shows a light micrograph of crystal of iodine, where molecules display a regular arrangement of equally spaced items within a lattice. Alright, next type of substances is called covalent network crystals. A covalent network crystal is a solid in which the covalent bonds between atoms form an interwoven network. Diamond, the hardest naturally occurring substance on Earth, is an example of a covalent network crystal. The carbon atoms in a diamond molecule form a tetrahedral structure, as shown earlier in figure 2b here. Each carbon atom forms 4 single covalent bonds to other carbon atoms by way of sp3 hybrid orbitals. We have talked about the concept of hybrid orbitals in the previous sections, right? You still recall that? The network covalent bond is the source of the name for these crystals. We can predict some of the properties of covalent network crystals using diamond as a model. Covalent network crystals tend to have very high melting points and extreme hardness. The melting point of diamond is over 3,500 degrees Celsius. Therefore, the covalent bonding structure in a network solid must be very strong. You must have observed many hydrocarbon molecules that contain carbon-carbon covalent bonds, such as ethene or octane. The carbon-carbon bonds in diamond are so different than the carbon-carbon bonds in these molecules. However, the strength of diamond is result of its interlocking network structure, which is shown here in figure 6. So think of a strands of a braided rope. If you were to separate the individual strands, you would find that they are very not strong. Yet, when you braid these strands together, the rope is much stronger than any one strand. Since the items in diamond interlock, they do not move around easily. This accounts for the extreme hardness of the covalent network crystals. A large amount of energy is required to break the bonds in the covalent network crystal and melt it. The electrons in the covalent network crystals do not move freely through the crystal because the atoms and covalent bonds hold the electrons in place. Thus, covalent network crystals are not good conductors of electricity. Carbon atoms can also form other structures in addition to the structure found in diamond. For example, in figure 7, which shows different structures of solid carbon. Carbon atoms can form layers or sheets, one in the solid phase, such as in graphite, which is shown here in figure 7b, large spherical molecules in buckyballs, as shown here in figure 7c, and even long, thin carbon nanotubes, which is shown here in figure 7d. Graphite has very different properties from diamond. Graphite is slippery, black, and an electrical conductor. These differences are the result of the difference in bonding with graphite. The carbon atoms arranged in a hexagonal sheet. Each carbon atom in a sheet of graphite bonds to 3 other carbon atoms in a trigonal-planar arrangement. Therefore, electrons in the sp2 hybrid orbitals form the covalent bonds in graphite. This arrangement results in delocalized electrons in p orbitals that can move from one side of the sheets to the other, which accounts for the electroconductivity of graphite. Graphite also has strong covalent bonds along the plane of the graphite sheet, and weaker London dispersion forces hold the graphite layers together. In contrast, a buckyball consists of 60 carbon atoms arranged in a soccer ball-like structure. Its actual name is Buckminster Fullerene, in honor of Richard Buckminster Fuller, who built architectural dome of this shape. The carbon atoms link together to form a hollow, dome-shaped cage. Buckyballs are extremely stable structures that have very high melting points. In the past 15 or 20 years, buckyballs have become popular because they have many different applications. Uses for buckyballs include chemical sensors, photovoltaic cells, cosmetics, and vehicles for delivering pharmaceutical drugs to cells. Carbon nanotubes are very similar in structure to buckyballs, except that they have a cylindrical shape that is rolled at specific angles. The properties of nanotubes differ depends on their circumference, length, and twist. Nanotubes were discovered in 1991, and scientists are still learning more about the properties and applications of these structures. Most covalent network crystals comprise the elements and compounds of carbon and silicon. The element silicon belongs to the same group, group 14, as carbon in the periodic table. Silicon compounds make up most rocks, sand, and soil found on Earth. crystalline quartz is a covalent network crystal of the silica molecule. This is shown here in figure 8a. Quartz forms a regular structure of molecules within the crystal. So when you heat solid silica above its melting point and then cool it rapidly, solid glass forms. Glass has a much more disordered structure than quartz, which is shown here in figure 8b. Cooling molten glass quickly forms a structure that is not crystalline. In fact, glass more closely resembles a very viscous liquid than it does a crystalline solid. The properties of a glass can change depending on the addition of different additives. For example, boron silicate glass made of boron oxide and silica produces a glass that do not expand or contract much when its temperature changes. Borosilicate glass is commonly used in labware and cookware because it resists breaking when heated or cooled rapidly. Alright, next let's have a look at the concept of semiconductors. Transistors are essentially, next let's have a look at the concept of semiconductors. Transistors are essential components of electronic devices. As transistors have decreased in size, so has the size of electronic devices. While the capabilities of these devices have increased, we can listen to music, work at a computer, and watch television because of transistors. Transistors act as amplifiers and switches in electronic circuits. Semiconductors are essential components of transistors. Semiconductors consist of covalent crystals of elements such as silicon or germanium that conducts a small amount of electrical currents in standard conditions. When we increase the temperature slightly, the conductivity increases significantly. Engineers modify silicon or germanium by adding a small amount of element such as arsenic or boron in a process called doping. This process allows engineers to create semiconductors with specific conductive properties. The items in a semiconductor have full valence electron shells, so electrons do not move from one item to another. Thus, semiconductors are normally non-conductors. Semiconductors are sometimes doped with arsenic, which has one more valence electron than silicon. A slight increase in temperature causes these additional electrons in arsenic to jump to a higher energy level. When the electrons are in an excited state, they move from item to item easily, and the semiconductor's conductivity increases. And this concept is illustrated here in figure 10a. We call this type of semiconductor an N-type semiconductor. Silicon can also be doped with boron, which has one less valence electron than silicon. The missing electron creates a hole around the boron items that electrons from surrounding items move to fill, which also increases the semiconductor's conductivity. And this type of semiconductor is called P-type semiconductor. So you can compare these two types of semiconductors here. Be careful with their differences. Okay, so this is pretty much about today's lesson. And please remember to complete the homework on Google Classroom and submit before the deadline, okay?